What we're going to try to do today is get through the anode. I hope to be able to get through the anode, and that'll leave a short lecture for chapter 8, the end of chapter 7 on Friday. And we might go ahead and start on chapter 8 since we're not going to have a test specifically over chapter 7. And again, I might kind of reverse engineer chapter 8 and 9, and what we're going to talk about, well, really not reverse engineer, but if you look on page 137, the 136 and 137, it's kind of those three bell curves, elongated bell curves, are what really we're going to park on for chapters 8 and 9. And what those describe is emission from the X-ray tube. So, if you flip over to page 138 and 139, you see representations of that. Also, if you flip over to page 140, you see those as well. So, what those are they're curves that represent emission from the X-ray tube. So we'll get to that possibly starting on Friday. But what we're going to do today is talk primarily about the anode. We've got a lot of stuff to talk about on it, the construction of the anode and the reason for the construction, and the different components in the anode itself. So it's a little bit more complicated than what the cathode is, the different moving parts that come with it. We're going to talk about the construction of the anode, what it's made of, and the reasons that it's made of what it's made of, which is primarily tungsten, and introduce one more concept of why it is that we use tungsten in both the cathode and the anode. So just to review what we did on today's was Friday, we talked about the external components. So we talked about support systems. We talked about the different types of support systems, most common of which and the most flexible would be the ceiling mounted systems, and those are the systems where you've got two sets of rails, 4 rails that are mounted perpendicular to each other, and then the overhead crane with the X-ray tube on it suspends from those things so that you can take those anywhere in the room and you can angle in any direction, rotate it in any direction. Very, very flexible. We had floor mounted systems which just run on tracks, a little unstable, very limited in what you could do with them. Then we have floor to ceiling mounted systems, still as limited as what the floor mounted systems are, just a little bit more stable. And then we have C-arm systems, which are come in a couple of different varieties. Some are most of the time they're going to be those portable fluoro units, or even stationary fluoro units, like what you would see in interventional radiography and interventional cardiac catheterization, but especially in special procedures. In a lot of cases, they'll use 2 C-arm systems that are, so that they can get one C-arm system shooting the AP and one shoot. I can't really do this, because this would be going across the patient in the wrong way, but they'd be capable of shooting AP and lateral fluoroscopy without moving anything, right? So it's just for efficiency so that they can see in both dimensions really quickly without having to move the C-arm. So then we talked about the protective housing. The protective housing protected you against the X-ray tube, protected the X-ray tube against you. So at the point of impact on the target, we get isotropic emissions. Isotropic just means equal intensity in all directions. We don't get emission from the X-ray tube or even the target that's isotropic, because the target itself is going to absorb some of those X-rays, right? But depending on which ways the X-rays are trying to go, if they're trying to go into the tungsten target, they're going to be absorbed immediately. But if they're trying to go out any place else, then you've got X-rays that are just going off in different directions. So we want to limit the emission from the protective housing to the window at the bottom, as right above the collimator housing, and that is the useful beam. So our issue there became, well, some of those X-ray photons may escape from other places, and that's what we refer to as leakage radiation. And the protective housing has to limit leakage radiation to 1 milligrade per hour at 1 meter. So the other things that it protects against is it's full of oil, and that oil provides, you may see it referred to as a thermal cushion. It's just cooling. That's all it is. So don't let the terminology throw you off. Thermal cushion just means that it's, you know, it provides a mechanism to cool the X-ray tube down. That's what it means. So it also provides or prevents against electric shock. It provides mechanical support, and it provides protection from rough handling. So then we talked about the envelope, and it's a vacuum tube, right? So it doesn't have, you know, don't mistake the oil inside of the protective housing for being inside of the X-ray tube. The X-ray tube is a vacuum tube. It has nothing in it except for the components. Doesn't have any gas or anything like that. It's completely evacuated. The oil is in the housing and not in the X-ray tube. Okay, so it's a vacuum tube. We talked about what happens if you lose that vacuum. You get a gassy tube, and with a gassy tube, we get erratic exposures. And the envelope can be made of glass or metal. If it's glass, it has to be Pyrex. If it's metal, then we have a benefit, and that is that as the tube ages, the filament vaporizes. As the filament vaporizes, it coats the inside of the X-ray tube, kind of like what it does a light bulb, and then it changes the potential from cathode to anode, and the electrons may go from, instead of cathode to anode, may go from the cathode to the glass, right? And that's a phenomenon we call arcing. And arcing is the main cause of instant tube failure, instant tube death. So your tube is done at that point. So the benefit of the metal is that if the metal envelope is that if they can overcome that tendency to want to go to the envelope instead of cathode to anode, then a little bit of tanning is not going to do anything to, you know, change that. So then we talked about the cathode. Parked on the cathode for a long time. So cathode is two filaments. Primarily it's going to be tungsten, but a little bit of alloy to keep it from being brittle, right? So it's two filaments inside of a focusing cup. The reason for the two filaments is not for backup systems. You can use it that way, but the primary reason that we have two filaments is one is small filament, so we can get good sharpness for recorded detail off of that filament. And we're going to talk a little bit more about that here in a bit. And the other is so that we can have a higher heat load. You know, the bigger the filament, we can stack more electrons on it. So if you're shooting some sort of big anatomy, you want to use large filament. If you're shooting for sharpness for recorded detail, you want to use small filament. Right, so we talked about what it, you know, an open filament or burnout filament looked like, so to speak, and that is if you were to make a reasonable exposure on one of those two filaments and it gave you tube overload, that just means you've got a burnout filament. It won't allow you to make an exposure because you can't get a space charge. So then we talked about the focusing cup. And the focusing cup has a small charge to kind of compress those electrons so that the electrons try to go across the tube and strike within, you know, a reasonable range, the anode in the part that we call the target. So the entire disc of the anode is not the target. The target is what we refer to as a focal tract. It's a small area all the way around the, you know, kind of the border of the outside of that disc. So more on that here in a bit. So it confines it to the focal tract, and in doing so, it increases sharpness for recorded detail. You know, we just kind of threw you know, just the memorization thing that, you know, if you're working with a tube that utilizes what we refer to as serial exposures, rapid exposures, one right after the other, then the focusing cup becomes the exposure switch within the X-ray tube, and that's what we refer to as grid control tube. So we talked about space charge effect. In context of this chapter, it is as many electrons as you can put around the focusing cup. It's the biggest space charge that you can create. You just can't stack any more electrons on it. And at the point of exposure, when you hit exposure, you know, the electrons jump across the tube and they evacuate that filament. You can put more electrons on the filament at that point, but you get to a point where you can't replace those electrons fast enough to get any more exposure, and that's what we refer to as saturation current. Saturation current is the highest exposure you can possibly get off of your X-ray tube. So space charge effect, saturation current. So the Focal spot is the actual area of bombardment. Small focal spot is 0.1 to 1 millimeters. Large focal spot is 0.3 to 2 millimeters. That's usually going to be determined by what you plan on doing with the X-ray tube. All right, so the focal spot can be very, very small. In mammo tubes, for example, we use what we refer to as a micro-focus tube, because what we're looking for is tiny calcifications inside of nothing but soft tissue. So we have to have very, very high spatial resolution in those. Special procedures, what we're looking for is maybe small aneurysms inside the blood vessels in the head. We have to have what we refer to as a fractional focal spot. So it's not as small as mammo, but it's smaller than diagnostic. And then diagnostic tubes, most of the time we can get by with that 0.3 to 2 millimeters. So, any questions on Friday's lecture? No? Okay, then we're going to spend probably the rest of the day today talking about the anode specifically. If you remember, I brought down different types of anodes in the X-ray tube on Friday. So what you're going to be using is rotating anode. Limited exposure like dental units will probably be stationary anode. If you've had any kind of dental x-rays, and I hope you have, otherwise you need to get your teeth taken care of, then you probably did not hear any kind of rotoring up, right? So it's just direct exposure. So limited exposure, you might run into those. I've only ever in my career seen one diagnostic x-ray machine that had a stationary anode. It was a very, very, very old portable, and the entire tube head was only, smaller than the size of the cup I drink out of. A little bitty thing. And we were kind of playing around with it. At the time, you could work as a student tech, and this was at a hospital that no longer exists. Yes, I killed a hospital. And they had this portable, and there were 2 student techs. We were in the same class, and we wanted to see if this machine would work because we'd never seen it move. And so we took it, and we're standing right by it, and we're pushing a button expecting to hear rotoring, and we never heard rotoring. And then it dawned on us the size of this tube housing was so small that it couldn't have much oil, and it certainly didn't have an induction motor. So we thought, okay, we need to take this film that we've been shooting on and run it through the processor, and sure enough, it was so dark you couldn't see through it, right? So we've been blasting ourselves, thinking that we were supposed to hear rotoring. It didn't have a rotor button, it just had an exposure button. So lesson learned. So you can have stationary. You're never going to work with stationary. You're going to have a rotating, rotating anode. So when we refer to the anode, we're referring to the entire positive end of the X-ray tube. So we've got supply of electrons from the filament. So that will be our negative end, and then we've got in comparison, the relatively positive end. And the anode includes not just the area of bombardment, which we're going to call the focal tract, and not just the entire disc, which we're going to call the disc. And we generally refer to that as, commonly as just the anode itself, but it's more than that. So what we've got is, I'm going to put in parentheses, disc, but you got to have something for it to rotate on, right? So that's going to involve 2 different things. One is a stem, and then the other would be some sort of bearings for it to rotate on, okay? So when you rotor up, what you do is you activate that induction motor that I brought down, right? So the induction motor slips over, you got the glass that surrounds all this, and the induction motor is considered to be a portion of the X-ray tube, but it's not in the X-ray tube. It's in the housing, but it's not in the X-ray tube. So it slips over the outside of that glass, and if you look on page I'm in the wrong chapter. If you look on page 119, Bushong shows you kind of a diagram of what the induction motor kind of sort of looks like. So think of it not exactly as you saw the induction motor, but think of it as being this thing, and it's got discrete individual electromagnets instead of, you know, one coil of wire going through a whole bunch of holes. Imagine it having just a number of induction motors. So it's got one here, and it's got one here. We're just going to do 4 of them. One here, and it's got one here. And the stem is there. And in the stem, you've got some sort of ferromagnetic material. Ferromagnetic, if you remember, easily attracts magnetism, right? So if we can control these electromagnets and turn them on just one at a time, then what will happen is they will draw that piece of ferromagnetic material towards it. So if we fire this one, it's going to try to come to here. And if once it gets going in that direction, we turn that one off, it's going to go to here. And if it gets close, we turn that one off and turn this one on, then it's going to have a tendency to go to there. It's going to continue to rotate. So what you're going to look for in test questions on the induction motor is that there are electromagnets that fire in sequence to accelerate the anode from 0 up to, I usually say 3,000 RPM. You know, Bushong is a little bit more specific, is probably more accurate, 3,400 RPM. So it goes from 0 to 3,400 RPM. And the commonality here that, you know, we both agree on is about a second. So if you go into clinicals tomorrow and you want to kind of, you know, test this, what you could do is set a very low exposure. You don't want to heat your tube up. And just go ahead and press the exposure button. If you press the exposure button, you will get an exposure, but you won't get an exposure until that accelerates up to speed, all right? You can bypass the prep button, just push the exposure button, and it'll work. But you're not going to get the beep until that gets up to speed. It's going to keep you from making an exposure until it gets up to speed. And that's protection for the tube to make sure that it's all the way up to speed before you make the exposure. Okay, so all of this is anode. That's anode, that's anode, that's anode, this is anode. Okay, so all of that is anode. All on the anode end of the X-ray tube. So we got to talk about each one of these things, and that, you know, the focal tract itself is anode. So we got to talk about each one of these things individually. All right. So the focal tract itself is going to be made of tungsten primarily, but it's also going to have some alloy in it for the same reason that we talked about before, and that is because tungsten is very brittle. So we want to give it a little bit of strength. And I'm going to, there are very few things that I'm going to say Bushong just isn't right about, but this is one of them. So, let's see. He says the target, let's see. Where is it? Here it is. So on page 117, it says that alloying the tungsten, usually with rhenium, gives it added mechanical support. Absolutely true. It's brittle. The rhenium gives it mechanical support. To withstand the stresses of high-speed rotation, yes, and the effects of repetitive thermal expansion and contraction, that is false. Tungsten does not warp when you heat it. It's one of the few things that does not change. It doesn't matter, well, until you get to the point of melting it. It doesn't expand, it doesn't contract whenever it's heated or cooled. Almost everything else does, right? So you heat water, well, water's a bad example. You heat water, what happens to it? It boils. It boils, it vaporizes, right? So it gets bigger. You get water cold enough, and what does it do? Freezes. And unfortunately, it expands there too. So water's weird, but everything else, you know, if you heat it up, it expands. If you cool it down, it contracts. I used earlier in the semester, you blow a balloon up and you completely fill the balloon, you stick it in a refrigerator, what happens? It's going to shrink down. You take it back out of the refrigerator and it's going to expand back out, right? So cold, contract, hot, expand. Tungsten doesn't do that. What's the significance of that? More significance in the filament than what we have in the anode, but if the anode itself is heated up to the point that it can expand, then it can also warp. Does that make sense? Mm-hmm. So, you know, we've got a disc, and the disc is going to be different thicknesses throughout the disc. So if the disc is different thicknesses, it can warp. In the anode, if we have the anode, specifically the filament, and it can heat up and it can expand, then where's it going to go? Do you think that a filament that gets hot and it does this number might have an effect on sharpness or recorded detail? A filament, or the focusing cup, only comes to here, then what's going on with the space charge out here? Right, now you hit it with a KVP, where those electrons going to go? All over, right? Not good for your sharpness or recorded detail. So, you know, it's an important thing to understand. You're never going to see it on a test question, but it's an important thing to understand that the tungsten does not warp. And that's a big reason why we use it. There's a number of reasons why we don't use it. That's not in the textbook, but we're going to get to the other ones here directly. The tip of this is already drying out, so put the lid on. Okay, so the other reasons that Bushong mentions, high atomic number. What's the significance of high atomic number? Well, how did we start this semester? How do we create X-rays?
Heat and electrons.
Okay, we're going to get heat in a minute. What are the two ways we create X-rays? Brims and characteristic, right? So electron interactions and characteristic. Let's start with brims. What specifically gives us the highest energy brims X-rays? So I'm going to get rid of my anode and I'm going to turn that into the nucleus of an atom. What gives us the highest? How do we get brims?
The interaction with the nucleus.
Interactions with the nucleus, right. So the closer to the nucleus we get, what happens? The electrons come screaming across the X-ray tube, approaching the speed of light. What's that?
They change direction.
They change direction. So you're driving down the road, and you whip the wheel.
It's a sharp turn.
You make a sharp turn. What's going to happen to your velocity, your speed, your energy of your car? It's going to slow down. Right. Right. So these electrons coming in, approaching the speed of light, maybe half of the speed of light, they're really moving across the tube. And they change directions, then that energy has to go somewhere, and that is going to be an X-ray photon. Right? So what controlled the energy of that photon? How close it was to the nucleus and how much energy it lost, right? So now back to atomic number. What do you know about atomic number? The higher the atomic number, the bigger the nucleus, and the bigger the gravitational pull. Now we got Venus instead of Mercury, right? We got a great big fat nucleus with a big gravitational pull, so to speak. So the electron gets close to it, it can lose more energy, and we can have a higher energy X-ray photon. We need high atomic number. But that isn't everything. Okay, so if you'll flip back to your elemental table. Alright, I gotta find it.
$37.
37, thank you. So if you look on page 37, he's got it highlighted for you. The chemical symbol for tungsten is a W. So what's the atomic number of tungsten?
74.
74, right. So it's got 74 protons, right? 74 protons. Protons determine the atomic number. So look 1, 2, 3, 4, 5 places over to the right of tungsten, and what do you run into?
Gold.
Gold, right. So gold would make a better target, right? I'm getting a yeah and a
I mean, it would melt.
It melts.
That's the
Yeah,
problem.
it couldn't
That's the
handle
problem.
what tungsten could handle.
Would it be better from an atomic number standpoint? Yes, absolutely. Now, look over from gold, 1, 2, 3 places. What do you run into?
Lead.
Lead. What does it take to melt lead? You know, it don't melt for nothing. You can pretty much melt it on the stovetop. So from a characteristic standpoint, would it be good? It'd be phenomenal. But how many exposures you gonna get off of a lead target? One, and you're gonna be done, right? So we have to have two things. We have to have a good big atomic number, but we have to have something that'll, you know, handle a big heat load. So back over to page 117, it has a high melting point. So we've got 3,400 degrees Celsius. You know, we do Fahrenheit here, right? So what is that in Fahrenheit? Oh, yeah, exactly. I don't really care. It's a lot. It's a lot more than 3,400, right? So it's 3,400 degrees Celsius is a melting point. So is it going to melt on its own single exposure? No, it's going to last a long time. So we have to have a big nucleus, and we have to have a high melting point. And as he doesn't really mention, we have to have something that's not going to distort. But we can't put all that heat in one place, so we've got to be able to conduct it, right? So it gives us all four of those things. It doesn't warp, it doesn't melt easily, it conducts well, and what was the other one? Oh, yeah, high atomic number, right? So that's brims. When we talked about as we increased our atomic number, what happened to our electron cloud around the nucleus of the atom? Not our thermionic emissions, but around the nucleus. It kind of collapsed in on it, right? So that the element itself didn't necessarily get that much bigger as atomic number went up, size-wise. Weight-wise it did, nucleus-wise it did. But what happened was they got closer together, right? So we've got more electron targets, not really considering that we're just shooting for the inner shell, but they're tight, right? So we've got more efficient brims by a long shot, maybe a little bit more efficient characteristic as well. So it's good for X-ray production. It doesn't melt, it doesn't warp, and it conducts well. Okay, so those are all the reasons for the tungsten. The reason that we rotate the anode is to aid in the conduction. So let's say we've got an anode. You know, we've got an anode face, and the only place that we place the electrons is here. We don't rotate it. Then what do we get?
Melting?
Melting. We get that, you know, that stationary anode that I showed you. Eventually it's going to melt. A lot of exposure's going to etch first, and then over time it's just going to melt. But if we rotate the anode, instead of placing all that heat right there, we take that anode and we rotate it around. What's the overall size of, not our focal spot? The focal spot size is not going to change, but our area of bombardment is massive now, right? So we're going to take that heat and we're going to spread it out over a much larger area. What's the purpose for that? Well, what's the main thing that kills the tube? Heat. So if we can spread it out, instead of bombarding in one place, we bombard in a big place, then what happens to our heat load? It reduces. So what's the purpose for rotating as fast as we do?
Getting rid of heat as fast as possible.
We're spreading the heat out as quickly as possible, right? So we're spreading it out so fast that, you know, we don't get to a point where we're going to, you know, melt the anode in a specific place.
It doesn't have time to heat up.
Right, it doesn't have as much of a time to heat up. we use this in a lot of things, and so anybody ever seen it's a airplane, it's called an A-10 Warthog. Anybody ever seen that? Ugliest airplane in the Air Force inventory, my favorite airplane, okay? So it's an attack airplane, and the airplane was built around a gun, all right? And it's what you refer to as a Gatling gun. If you've ever seen Western, you've seen a Gatling gun, they crank a crank, and two things happen, and that's that it fires a bullet, but the barrels rotate. Okay, so the A-10 works off the same principle. So it's got, I think, 7 barrels on it. This thing's like 30 feet long, this gun is, and it shoots a 30 caliber bullet. And as it fires, the barrels rotate so that each barrel is cooling while the one barrel is firing, okay? Same principle, we're rotating that thing around so that we're cooling as we're heating one spot, okay? So a couple of questions here. All right, so we've got a disc size that's specific, and we rotate it at a specific speed for those two reasons, to spread out the heat and spread out the heat more efficiently. Okay, so most of your tubes are going to follow the, what Bushong said, about 3,400 RPM, and your disc size is going to be about the size of the disc that I passed around on Friday. Okay, so is there a way that you could further increase the heat capacity of the X-ray tube just on the anode itself? We used a relatively large disc for a very small focal spot. Is there something else we could do? Following the same rule, what if our disc was this big and our focal tract was that big?
You increase the area.
You increase the area, right? So you have more room to spread it out. So that's one thing. Increase the heat load by increasing the size of the disc, right? Could you rotate that even faster in order to also spread it out? The answer is yeah. Yeah, so the larger the disc and the faster you spin it, the more you spread that heat out, the higher the heat load your X-ray tube is capable of. Okay, so CT tubes, special procedures tubes, they're right here. All right, your diagnostic tubes are like this. Okay, so you can still have the same focal spot size, it's just that you've got more area to spread all that out with. Okay, so let's go back down to our small disc. The disc that I passed around on Friday, I think was all tungsten. Not all of them will be all tungsten for a couple of different reasons. One is tungsten's heavy. You felt that anode, right? It's heavy. So the heavier something is, the harder it is to rotate. So what they might do is make the focal tract, and that's just the area of bombardment, out of tungsten, and they might embed it into a lighter material. It still has a high melting point, and it still has good conductivity where the heat will spread out. But it might be, Bushong says graphite. Graphite's probably going to be a backing for a reason I'll talk about in a minute. But molybdenum is a common alloy that they'll use, or a disc face that they'll use. The purpose for the molybdenum is to allow the heat to spread out, not just around the focal tract, but around the entire face of the anode. Okay, so now you've got the area of bombardment catching all the heat, but it can go all over the place, right? Now looking at the anode from this dimension, what you might have is a backing that's made out of graphite. And graphite is a poor conductor of electricity. Okay, so we just kind of slammed on the brakes. What are the ways that we reduce heat in the X-ray tube? Conduction, convection, thermal radiation, right? So thermal radiation from here down to the glass, conduction into the oil, but also conduction all the way around this. For right now, our convection just doesn't play a part. But here's the thing, is that we want to conduct the heat as much as we can around the face of the anode, but we don't want to put it right here. We don't want it going down the stem in as much as we can stop it. It's got to go down the stem, you know, because this entire thing is inside of the X-ray tube, right? So you're going to get some thermal radiation. It's going to get to this down here. But the problem is these bearings, and they could be a number of different configurations. They could be ball bearings, they could be needle bearings, they could be any kind of bearing. They're greased to make them roll easy, and eventually that grease is going to vaporize. You know, you change the oil in your car. If you've never done oil changes in your car, your oil gets exhausted. You know, when you pour it in, it's yellow. When you drain it out, it's black. Okay, if it's been cooked long enough, it just it exhausts. So it's the same thing's going to happen to these. Why? Because thermal radiation gets hot, right? So eventually that grease is going to it's going to be exhausted, and once it gets exhausted, it's going to be less efficient. So the bearings have a harder time turning, and eventually you get a tube that's old enough, you'll hear it. You get this grinding sound every time you rotor up. So as you rotor up, if the grease on the bearings are exhausted because of the heat, what's going to happen is the rotation of that anode is going to slow down some, which is going to cause you to build up more heat, which is going to affect your bearings, which is going to cause it to slow down some and build up heat. And it's a negative cycle that eventually is going to cause you to, the bearings will eventually seize up, weld together, and at that point you've got a stationary anode. Okay, so you got a stationary anode, your tube needs to be replaced. Generally speaking, whenever you start hearing that grinding sound, then that's an indication that your tube needs to be replaced. They're expensive though, so sometimes they delay a little bit. You may have to deal with a grinding sounding tube for a little bit of time. Okay, so just to bring some context to it. You ever been sitting at a red light and a car pulls up next to you and they just sound like they're dragging something? Okay, you got one of two things going on there. Either you're sitting there and you hear and the car pulls up and it stops, right? The grinding sound stops. So you got one of two things going on there. Either the brakes really need to be changed out. Your brakes, you've got a ceramic surface that touches a metal surface, and eventually the screws in that ceramic will be exposed, and then you've got metal on metal, and that's what you're hearing. Okay, that's causing that grinding sound. If whenever they take off and they're not pushing on the brakes, it's not the brakes. You've got bearings inside of your wheels as well, and because you've been driving down the road for 100,000 miles, that grease will wear out and your wheel bearings will start to grind like that. So that's exactly what your X-ray tube sounds like, is that somebody in a car that needs wheel bearings replaced just pulled up beside you. It gives you the same stop that feeling. So that's two things. One is that's what it's going to sound like. Number two is, that's how you diagnose your car if you start having a grinding sound while you're driving down the road. If you hit your brakes and it grinds, that's your brakes. You need new brakes. If you're not on your brakes and you're hearing a grinding sound, you need new wheel bearings. So, auto maintenance 101. Bringing a real life thing to you, Anyway. All right, so where am I in my notes? Okay, so we covered a lot of stuff already. All right, so high atomic number, large nucleus, memo tubes. Okay, memo tubes. All right, so we talked about the focal spot size of memo tubes, what we refer to as microfocus tubes. Also in MAMO, what the disc itself will be made out of, because it's lighter, easier to turn, the entire disc may be made of molybdenum. Molybdenum has a much lower atomic number than what does tungsten. Okay, so why might, this is your critical thinking question of the day, why might we use molybdenum in mammo tubes instead of tungsten?
We don't
They
want
don't
as
need
high
as high
energy.
KVP.
We don't need as high KVP. Very good. We don't need as high KVP because what are we shooting?
It's like 25
Soft
minutes.
tissue.
It's all soft tissue. It's all soft tissue. And what we're looking for is micro calcifications. Okay, so we definitely don't want to use high KVP on breast, because what we've got is, when I say micro calcifications, take your pen and just put a dot on your paper. I don't mean a scribble dot, I mean that's the size that we're looking for, okay? So if we use high KVP, then we can burn that out pretty easily, right? Even with digital imaging, digital processing, it can make it difficult to see. So we need very high resolution, and we need low KVP in order to visualize that with good processing algorithms to bring out the contrast so we can see those. So we use molybdenum because we don't need that 69.5 KVP characteristic X-ray photon. We don't even need those high energy BRIMS photons. We're not going to be shooting with more than 25 at the absolute top, maybe, probably, I don't know, I've never done mammo, but maybe 40 KVP, absolute top. So it's going to be low KVP. We don't need tungsten. We're going to use molybdenum for those. All right, so rotation of anode, high capacity induction motor outside the tube, electromagnets, fire. Oh, yeah, okay. All right, so we've got I need my induction motor back. So we've got our induction motor with the electromagnets, in different places. We've got our anode. We've got the ferromagnetic material inside of it. And first off, before I start into this, how many x-rays are you creating with your car? Exactly none, right? But yet you can still wear out your wheel bearings. Why? Friction. It's just friction. It's friction. It's friction driving down the road. Your tires on the road creating a lot of heat. It's also the friction of those bearings rolling around in there, creating a lot of heat. All right. So just the time spinning the anode will create heat. Even if we don't create a space charge, we still create heat just rotating the anode. Okay. So we're not going to rotate the anode without creating a space charge in the prep stage. But once we make the exposure, where's our space charge?
On the focus cup.
It's gone. It's gone. We make our exposure, we don't have a space charge anymore, right? You get off the button. Do you hear your rotors still rotating? For a short time.
Yeah, it's like
For a short time, right? So y'all noticed whenever I passed the tube around and you rotated the tube, what did you notice about the anode as you rotated the tube?
It's like fixed.
It's insanely balanced, right? So you rotate it and it doesn't move all that much. Okay, so taking that the other way around, if you get it going 3,400 RPM and then you let it go, how long is it going to rotate? Forever. Yeah, it'll rotate a long time. So what's happening as you rotate? Friction is creating more heat. So do you want that to continue to rotate? And the answer is no. So your induction motor is going to do two things. We've talked about one of them. It's going to, when we push the prep button, we get heating of the filament to create a space charge, and we rotate the anode from 0 to 3,400 RPM in about a second, right? But we make the exposure, and what you don't hear is this thing rotating forever. It would. I've worked with a machine. All these problems I'm talking about with the machine is one machine. It was a great machine, but it had quirks. But what happens after you make your exposure is the induction motor kicks back in and it fires in reverse order to take you from that 3,400 RPM back down to 0. Okay, and most of the time that's going to happen within 5 seconds. So you make your exposure and you'll hear one beep and then you'll hear possibly a second beep whenever the rotor stops. Okay, and if you don't hear the beep, generally you can hear the end of the rotation. So it fires, let's say it fires this way to start the rotation. Once you make your exposure, it starts rotating that way. Firing in sequence in the opposite direction to take you back down to 0 to prevent you from, overusing your bearings, creating more heat. Okay, so it actually does both. It starts the rotation and it ends the rotation. Minute tops, usually within 5 seconds. A lot of times within a second. There's just no reason to continue to rotate it. Okay. So any questions so far? I'm making some time. Any questions? I think we'll make it through anode. All right, so let's get a little bit more specific in the focal tract itself. Okay. So the focal tract is the actual area of bombardment on the disc. Okay. So again, the entire disc is not, the entire disc is not the target. The target is actually your focal tract. It's where you're aiming your electrons. It's where you want your bombardment to take place. Much smaller than what I've drawn here. All right, so your anode is going to come with an angulation, and that angulation is going to be anywhere from 5 to 20 degrees. So the degrees is, the smaller the number, the more vertical it is. So a 5-degree angulation would be almost completely vertical. Okay. So most of them are going to come in around 17 degrees, but it could be 5 to 20. So if you're in, what that's going to control again is angulation, but it's also going to control your sharpness of recorded detail. So you've actually got two things that go into your sharpness of recorded detail. One is the size of the filament. The size of the filament is going to control the area of bombardment. So if we have large focal spot, we'll press the button for a large focal spot, we energize the large filament. If we use the small focal spot setting, then we are going to limit the area of bombardment to a much smaller area. Okay, that's what we use to control sharpness of recorded detail, is just filament size. Some tubes are what we refer to as bifocus tubes. And with bifocal tube, we touched on that on Friday. With bifocal tube, what we may have is we've got an anode angle here, and then it may go into a steeper angle. So it may be both 5 and 17 degrees. Large focal spot will be on the 17 degrees, small focal spot will be up here. Those are the, again, special procedures tubes. You're probably not going to work with one of those unless you work in special procedures, cardiac cath lab or something like that. So that's what we refer to as a bifocal tube, or bi-angle anode. I'm sorry. Any tube with 2 filaments is a bifocal tube. That'd be a bi-angle anode. Okay. So, all right. Now, what we have, let's say if I could draw this on a perfect 45-degree angle, if I were to draw our electron stream coming across, impacting, and let's say our X-ray beam was reflective of our stream, our X-ray beam was, reflective of our stream of electrons. I kind of tapered that off a little bit. Then the stream of electrons would be exactly the same size. It's not in this case because I'm not at a perfect 45-degree angle. I can't draw a straight line to save my life. But our stream of electrons, or stream of photons, will be the same size as our stream of electrons. Can you kind of see how that is? At 45-degree angles, that's what we get. When we come down to a 17-degree angle, then we get this. Our stream of photons is smaller than our stream of electrons. Okay? Everybody good with that so far? Let me erase the small focal spot stream so that it's not confusing. So our photons, those are X-rays, electrons impact a large area, and what we get is a small stream of photons as a result of the angulation on the anode. So the more shallow the angle of the anode, the wider the stream of X-ray photons. Okay, everybody good with that so far?
Would they go straight down, or would they?
No, they go all over the place. It's just for demonstration.
Okay.
Yeah, I mean, they're going to come out divergently, and but this is just for demonstration purposes. Okay. So if this stream of photons, and it does, controls what ultimately controls our sharpness or recorded detail, which one are we going to get better sharpness off of? A nice fine stream of photons, or a big fat stream of photons? Everybody agree to that? The fine one? And you're right. So what you've got is small focal spot gives us a nice tight stream of photons as opposed to, this. So we've got a light bulb compared to a fluorescent light. Okay, so then what we have in what controls our sharpness or recorded detail inherent in our X-ray tube is two things. It's not just the filament size, is the angulation of the anode. The steeper the angulation of the anode, the higher the sharpness or recorded detail, the better sharpness we're going to have. Okay, so there's so Bushong will go into saying the benefit of angling the anode is that we can use a relatively large area of bombardment and have and this is what we refer to as the actual focal spot. And it would give us a fine stream of photons that we would refer to as the effective focal spot. And it's not really a stream of photons as much as what it would be is if, if you were looking straight onto the anode, you could see the actual area of bombardment, right? You're just looking straight onto the anode. Your eyes are replacing the cathode into the X-ray tube. You're staring straight down onto it. You can see the area of bombardment. It's quite large. But the projected focal spot, which is what we refer to as the effective focal spot, would be as if the patient was laying flat on their back and they're looking up into the X-ray tube. So they're looking up into the X-ray tube. I don't know who belongs to this. Oh, come on, I don't want to open it, I just want it to get longer. I don't think it will. I'm going to tear up some, well, here we go. All right, so your eyes are the anode. So how big is this? It's pretty big, right? I turn it like that, how big does it look?
A little bit small.
A lot smaller, right. So what we use is, this is what we refer to as the line focus principle. We use a very large, a larger area of bombardment, right? What would be the significance of a large area of bombardment? Heat dispersion. Yeah, we can spread the heat out on a bigger area, but we get the benefit of the smaller projected focal spot to give us increased sharpness recorded detail. That's what we refer to as the line focus principle. And, It makes it sound like it's an engineering marvel that they did this thing. And it's really not. It's the only way we could make the X-ray tube. You know, if we put, you know, let's say the patient would, that thing got nothing left. If we put the patient over here, we projected the X-ray tube, the X-ray beam back straight towards the cathode, what are you gonna see on every X-ray image? You're gonna see the cathode, the entire cathode, focusing cup, you're gonna see both filaments, you're gonna see everything that's on the cathode end of the X-ray tube. So we have to have it projected down like that. The benefit that we get out of it is we can increase our heat load and at the same time increase our sharpness of recorded detail. Again, that is the line focus principle. Okay? And what the definition of the line focus principle is that we utilize, it's the difference between the actual area of bombardment, the actual focal spot, and the projected focal spot, which is our effective focal spot. We use a large area of bombardment to project a beam that gives us sharper, sharper image, higher, better sharpness recorded detail, line focus principle. The unfortunate consequence of this is shown on page 121, and Amy's probably talked about this already. So if you look on page 121, what you find is that because our X-ray tube, or our anode rather, is made of tungsten, and tungsten is, it's a heavy metal. And you know what you know about metal, right? How's it look on X-rays?
Solid white.
Solid. You can't see through it at all, right? So let's say our window is here. A window is what's supposed to, limit the isotropic emissions to the useful beam, right? So our window is here. So if I create an X-ray photon right there, can it go out that portion of the window? Can it? Bounce right off the bottom, the heel of the anode? It probably can. What about this one up here? Is it gonna make it out? Probably not. Could this one bounce off and go out of the cathode into the X-ray tube? Yeah. Could this one? Again, yeah, it absolutely can. So in this very crude drawing, how many X-ray photons did we emit between the one that had to penetrate the entire anode and the one that didn't have to penetrate that entire anode? How many X-ray photons did we get here? One. And so over here, X-rays, remember, X-ray created right on the surface of the anode. It's not that they go, and bounce off of a atom, halfway through the anode. They're created right on the anode face. So how many do we get going out the window on that end? Two, exactly. So comparing the anode end of the X-ray tube to the cathode end of the X-ray tube, which end has a higher intensity if intensity is mass and mass is numbers? Cathode end of the X-ray tube. We call this the bingo, anode hill effect. Right, so how do we use the anode hill effect? How might we use it to our benefit? It's an unfortunate thing, but
Cathode side on that thicker part.
put the cathode side over the thicker part of the anatomy. So you're shooting a T-spine, the abdominal end of the T-spine goes down here, right? You're shooting a foot, proximal end of the foot goes down here. You get a greater intensity coming out of that end of the X-ray tube, so you put it over the thicker anatomy. Now here's the thing about the anode hill effect, is that that's not the end of it, all right? So it's not just the intensity between cathode and anode end of the X-ray tube. It's part of it. Cathode end, you've got greater intensity than the anode end. I always, when I was in school, I'll be honest with you, I tried to flip that around. Anode heel effect, and we'll call it an anode. So, you know, intensity is greater on the anode end. No, it's intensity greater on the cathode end. Okay, so don't flip that around. But the rub is that, you know, not really going to draw this out because this is really next semester, but I want it to be planted, is that there's also a difference in sharpness or recorded detail between the cathode and anode end of the X-ray tube. You get better detail on the anode end than what you get on the cathode end. More intensity, less detail, less intensity, more detail. So what causes the difference in intensity between cathode and anode end? What causes a decrease in intensity at all between where we create X-rays and X-rays come out of the X-ray tube? I got about three things at the same time.
Is it the metal?
It's the metal creating, I'll give you a hint, absorption of low energy X-ray photons.
So maybe
Not KVP, that's creation, absorption of low, huh? Filtration, bingo, filtration. So in the anode heel effect, what provides the filtration? Why the difference? It is filtration, but what's creating the filtration? No. The anode itself is the inherent filtration that's creating the difference between the cathode and anode end of the X-ray tube. Okay? So anode heel effect. Here's the other thing about it. All right, so let me kind of give the numbers that are a little bit more representative of what Bushong has drawn here. So he says on the anode end that we may have as little as 75%. The center is 100% of what you want, and the cathode end, what does he say? 120. Yeah, thank you. 120%. Okay, so the center of the X-ray beam is what we want. Cathode end of the X-ray tube, we get more than what we want. Anode end of the X-ray tube, we get less than what we want. Okay, so then what we have, you know, it's not just three things. It goes 100%, 101, 102, 103, 104, and so forth until we get to 120. It goes from 100 to 99, 98, 97, 96, and so forth. Right? So let's draw this out a little bit further. I say we shot this particular image at, you know, just bear with me. I know this is not to scale, but let's say this is 40 inches. And we wanted to cover an image receptor that is this big. Okay? So, I don't know, what we should, maybe APL spine. Right? Now we want to do a chest X-ray. What distance do we want for a chest X-ray? 72 inches. So now my image receptor, which is the same size, is going to be that big. You know, it's roughly the same size, right? All right. So what do we call the spreading out of the X-ray beam? Divergence. Okay, so now where is my 120?
not even on the IR.
Bingo. So what are your rules for collimation? Two things. Always collimate to the size of the anatomy and never larger than the IR. Right. So now my X-ray beam, we're going to collimate down to that. Okay.
Much closer to what we want.
Much closer, by that you mean to the 100%?
100%, yeah.
Right. So is the anode heel effect as significant at low OIDs as what it is at large SIDs? How bad is it at 40 inches? Well, it goes from 75 to 120. What swing is that? 55% change between cathode and anode end of the X-ray tube, or 45% change? 45% change, right? So that 45% change is now down to, you know, if 100% is still here, that may be 110, and this may be 90.
Another 20.
So is it more significant at low OIDs or long OIDs? At low. At low. At low is bad, right?
Yeah.
You drop it down to 30 inches, it even gets worse. At 72 inches, how bad is it? Not as bad. Not as bad, right? Because you're using more of the middle of the X-ray beam, so it's not as bad. So, you know, we tend to kind of end the discussion on anode hill effect as the difference in intensity between the cathode and the anode end of the X-ray tube, and that's part of it. But the other parts are, you know, two things. One is that it gets better with increased SIDs. By better, it means that the cathode and anode end of the X-ray tube emission are more similar, and also we get a decrease in sharpness or recorded detail on the cathode end as opposed to the anode end. So we're going to hit that again next semester, just kind of planting seeds on those. But the intensity difference is really pretty much where we're landing right now. The intensity difference is worse at low OIDs, but it's always present. Cathode end always more than anode end. Right? Whew.
How can you tell which side is the cathode end and which is the anode?
Yeah,
It's
good
on the
question.
housing and everything.
Yeah, good question. So what you can do is you can look on the X-ray tube, and a lot of X-ray tubes are going to be marked with it. So it may say cathode, and it may say anode, and it might instead have a plus and a negative, right? So the plus would be the cathode end, or plus would be the anode end.
Anode.
Yeah, yeah. So either one of those two, and some of them the stickers have come off. And most rooms are going to be set up for most exams to take advantage of the anode hill effect. So when we say utilize anode hill effect, it just means position the patient as you always would in most cases. Okay. All right. So what's our time now? Lost my phone. We're a little over an hour, aren't we? Okay. Y'all feeling kind of saturated? Okay. All right. All right, we'll finish up chapter 7 on Friday, and we'll press on into chapter 8, and we'll finish up chapter 8 on Wednesday of next week.